Hi, I'm Mark Barsamian with the Math Department at Ohio University in Athens, Ohio. This is the third in a collection of videos for a one-semester course in calculus. Here at Ohio University, it's our Math 1350 survey of calculus. In the first two videos, Limits Video A and Limits Video B, I introduced the idea of limits and discussed examples of limits for functions given by graphs in Limits Video A and for functions given by formulas in Limits Video B. In this third video, I'll be again discussing limits from an analytical perspective, that is, limits of functions given by formulas, not by graphs. But in this video, the formulas will be piecewise defined formulas, so that will complicate the computation of the limits. Our topics for this video will include reviewing the notation for piecewise defined functions, expressing the absolute value as a piecewise defined function, and considering two examples of limits of piecewise defined functions. Now, in the video, we won't go in that order. In fact, we'll just dive right into the two examples, and this stuff, the review of piecewise defined functions, will come up as we go. Now remember that you can view or download the PDF file produced in the making of this video by going to the link provided in the description of the YouTube video. Math 1350 students at Ohio University can also find a link on the course webpage. We'll need some stuff from Limits Video A. This symbol, the limit as x approaches c of f of x equals L, means the following. As x gets closer and closer to c, but not equal to c, the value of f of x gets closer and closer to L, and may actually equal L. And remember the difference between the symbols f of c and the limit as x approaches c of f of x. The symbol f of c denotes the y value at the x value, x equals c. Whereas this symbol, the limit as x approaches c of f of x, tells us about the trend in the y values as x gets closer and closer to c. In the current video, we'll also be dealing with limits from the left and right. Remember that this symbol, spoken the limit as x approaches c from the left of f of x equals L, means this. As x gets closer and closer to c but less than c, the value of f of x gets closer and closer to L, and may actually equal L. And remember the graphical significance. That means that the graph of f appears to be heading for the location xy equals c comma L. That's that c and that L. It appears to be heading for that location from the left. And remember that there is an analogous definition for the limit from the right. And very important in the current video will be this definition of the limit as a three-part test involving one-sided limits. So remember that to say that the limit as x approaches c of f of x equals L means that the function has to pass this three-part test. That is, test A, the limit from the left has to exist. Test B is the limit from the right has to exist. And test C is the limits from the left and right have to match with value L. So the limit from the left has to equal some number L, and the limit from the right has to also equal that same number L. Useful properties from Limits Video B, Theorems 2 and 3 are properties of limits that allow us to find complicated limits in certain situations by replacing them with less complicated limits, such as this. One of the most important limit properties that we'll use in this current video is this one, Theorem 3, that says if you have a polynomial function f, then the limit as x approaches c of f of x can be found by just simply substituting in x equals c to compute a y value, f of c. In this video, we'll be continuing an analytic approach to limit. That is, the function f is described by a formula, not a graph, and we'll be discussing the two examples involving piecewise defined functions. So we'll just dive right in with the examples. So in example 1, we have f given by this messy expression. Now I should speak this so you know what this, how this symbol is spoken. This is read f of x is equal to minus 2x plus 10 when x is less than or equal to 3, but it's equal to x squared when x is greater than 3. So any mathematical symbol can be spoken, and this is one that can be spoken. Now our job in this example is to do these 5 things. Find f of 3, find the limit as x approaches 3 from the left of f of x, and find the limit as x approaches 3 from the right of f of x. And finally, find the limit as x approaches 3 of f of x, and lastly, to illustrate those earlier results with a graph. Well, we need to start by making sure that we understand what the notation for function f of x really means. This function is an example of a piecewise-defined function. That is, the function is described by different formulas on different pieces of the domain. The notation is very much abbreviated. So to understand how the function works, it's often helpful to think of it in a less abbreviated form. So this abbreviated expression means this: f of x equals minus 2x plus 10 when x is less than or equal to 3, and f of x equals x squared when x is greater than 3. So this is just a slightly less abbreviated form of what we saw earlier. But I find it's even more helpful to think of the function in a form that reflects how one uses the formula for a piecewise-defined function. That is, given an input x, one first determines which piece of the domain x is in, and then uses the appropriate formula to compute the output. This process would be better described with the following 2 sentences. If x is less than or equal to 3, then f of x is computed using this formula: f of x equals minus 2x plus 10. But if x is greater than 3, then f of x is computed using this formula: f of x equals x squared. So these 2 sentences mean exactly the same as the symbolic expression we started with, this thing. But these 2 sentences better reflect how we're actually going to use f of x. Now we're ready to solve the problem. Question A said to find f of 3. Well, to do that, we note that because this inequality, 3 is less than or equal to 3, is true, then we use this formula to compute the output. So to compute f of 3, we use the appropriate formula and replace that with this expression. We took the formula f of x equals minus 2x plus 10, and we substituted in x equals 3. So we get the result 4. So f of 3 equals 4. Question B says, find the limit as x approaches 3 from the left of f of x. Well, to do that, we have to first note that this symbol, x approaches 3 from the left, tells us that we should be considering x values that are getting closer and closer to 3, but less than 3. Well, for these x values, for x is less than 3, the formula for f of x is the following: f of x equals minus 2x plus 10. So we write down what we're going to compute. We're going to compute this limit, and then we swap out the formula for f of x, the appropriate formula. So there's our f of x. We use the appropriate formula, which is that one, and we swap out that part of the expression. Notice that the rest of the expression is still there. We still have that frame, that limit as x approaches 3 from the left, is still parked out in front. All we did was we swapped out f of x and replaced it with the appropriate formula. Now let's zoom out. What we've got here is the limit of a polynomial. Our theorem 3 that we discussed in the previous video, theorem 3 says, again, for a polynomial function f, the limit as x approaches c of f of x can be computed by simply substituting in x equals c. That is, the value of the limit just turns out to equal the value that's the y value. So theorem 3 tells us that we can replace this limit expression with this expression that we obtained by just simply substituting in x equals 3. So the end result is that this limit that we were told to compute just turns out to equal this number 4. Notice a couple things here. First of all, the way that I lay out this problem. This is what I referred to in the previous video as kind of an accordion form. We start our line with the symbol for the thing that we are supposed to compute, and we end that line with the value that it actually has. So this whole line tells us that the value of this limit is 4, but the whole line can be spoken as a big sentence. That would be the limit as x approaches 3 from the left of f of x equals this stuff which equals this stuff, which equals 4. So that's one great big mathematical sentence. Another thing to notice is the appearance of the limit symbol. Our original job was to find a limit, so the limit symbol was part of that. In the second step, we have that limit expression because all we did was we swapped out f of x. So we have to remember to leave the limit symbol in because we didn't actually compute the limit yet. It's not until here, after we've used theorem 3, that we can stop writing the limit expression. In question C, we're supposed to find the limit as x approaches 3 from the right of f of x. Well, remember that this symbol, x approaches 3 from the right, tells us that we're supposed to be considering x values that are getting closer and closer to 3, but greater than 3. Well, for those values of x, we have to use this formula, f of x equals x squared. Remember, when x is greater than 3, f of x is computing using this formula, f of x equals x squared. So we compute the limit as we have done in the past. We start by writing down the expression that we're supposed to find, that limit expression, and then we swap out the f of x and replace it with the appropriate formula, so that f of x gets replaced with that formula for the function f of x. So again, the limit expression stays out front. We haven't done the limit yet. We've just swapped in the appropriate formula. Now we zoom out and observe that we are finding the limit of a polynomial. Theorem 3 tells us that we can do that by just simply substituting in x equals 3. And the result is that this limit equals the number 9. Question D says, find the two-sided limit, that is, the limit as x approaches 3 of f of x. Well, that's straightforward. This limit does not exist because the left and right limits don't match. Remember the three-part test for limit. For this limit to exist, the left limit has to exist, the right limit has to exist, and the left and right limits have to match. So that's why the limit does not exist. Question E says to illustrate our results of the previous parts with a graph of f of x. Well, to draw the graph of f of x, it's helpful to first draw separate graphs for each of the formulas that make up the description of f of x, and then use these separate graphs to build a single graph of f of x. So let's go back up and look at the description of f of x. We have this equation, f of x equals minus 2x plus 10, and we have this equation, f of x equals x squared. So we're going to make a graph of y equals minus 2x plus 10, and we're going to make a graph of y equals x squared, and those two separate graphs are going to go into making a graph of the function f of x. So here on the left we have the graph of y equals minus 2x plus 10. Here on the right we have the graph of y equals x squared. Now those two graphs go into making the graph of f of x, so down below we have the graph of f of x. Now notice that for x values less than or equal to x equals 3, the graph of f of x is taken from that green graph. For y values greater than x equals 3, the graph of f of x is taken from that red graph. Well, there's a graph of f of x, but our job was not just simply to draw the graph, it was to illustrate the earlier results. So how do we illustrate those results? Well, what were those results? The result of question A was f of 3 equals 4. That's an equation, f of 3 equals 4, that corresponds to a point being on the graph, the point with x, y coordinates 3, 4. So to illustrate the result of question A, we should point out that there is a point on the graph at the location x, y equals 3, 4. So we've illustrated the result of question A. How do we illustrate the result of question B? The result of question B was that this limit as x approaches 3 from the left of f of x was the number 4. Well, that expression, the fact that that limit exists and equals 4, remember, has a graphical significance. That tells us that as x is getting closer and closer to 3 from the left, the graph of f of x is heading for the location with x, y coordinates 3, 4. So we can highlight that kind of behavior on the graph. There I've drawn some symbols that sort of highlight that the graph is heading for this location, but we really should hit the reader over the head with this and say very clearly what they're supposed to observe in this drawing. So there we've highlighted the behavior on the graph by drawing some additional annotations and even some words so that the reader really notices what we want them to notice. Now, how do we illustrate the result of question C? In question C, we found that the limit as x approaches 3 from the right of f of x was 9. Well, remember the graphical significance of that. That means that as x approaches 3 from the right, the graph is heading for the location with xy coordinates 3, 9. So we can highlight that behavior on the graph. So there we've drawn arrows that sort of highlight the fact that the graph is heading for that location. But again, I think we should really hit the reader over the head with this so that they notice what we want them to notice. So there's our final product, the graph of f of x with these additional annotations that highlight the results or illustrate the results of questions A, B, C, and D. Now notice one thing. In my words, I say that the graph is heading for the location xy equals 3, 4 from the left, and heading for the location xy equals 3, 9 from the right. I don't say heading for the point. It happens that there is a point at 3, 4, but there's not a point at 3, 9. So I definitely would not have wanted to say the point 3, 9 there. It definitely had to say location. Here I wanted to say location also because the idea of the limit is it's about the trend. It's not about what you actually find when you get there. So the fact that the limit from the left exists and equals the number 4 means that we're heading for this location. It doesn't matter that when we get there, there actually is a point there. It's just that the fact that we're heading there is enough. All right, that wraps up example 1. Let's go on to the next example. In example 2, we have this function. F of x equals x minus 11 divided by the absolute value of the quantity, x minus 11. So it's a very different looking formula. But then we have the same kinds of questions that we had in example 1. These 5 questions. Find f of 11, find the limit as x approaches 11 from the left of f of x, and so forth. Okay, well, as in the previous example, we have to start by making sure that we understand what the notation means. Now, you're all familiar with the behavior of the absolute value function when the thing inside is a number. So, for instance, the absolute value of 5 is 5. The absolute value of negative 7 is 7. Or the absolute value of 0 is 0. But you're probably not so familiar with the absolute value function in abstract settings, where the thing inside the absolute value involves a variable. The absolute value symbol actually represents a piecewise-defined function. Here it is. Here's the definition of the absolute value function. The absolute value of x equals x when x is greater than or equal to 0, but it equals minus x when x is less than 0. As we did in example 1, it's helpful to think of the function in a form that reflects how you use the formula for the absolute value. So here's the definition of the absolute value function in sentences. If x is greater than or equal to 0, then the absolute value is computed using this formula, absolute value of x equals x. If x is less than 0, then the absolute value is computed using this formula, absolute value of x is the negative of x. Now, in order to understand how the absolute value function is used when the thing inside is a more complicated expression, it's helpful to first consider what I call the empty version of the function. So here's the definition of the absolute value function in sentences, the empty version. So in this version, I've just simply replaced all of the x's in this version with empty parentheses. So if empty parentheses are greater than or equal to 0, then absolute value is computed using this formula. The absolute value of parentheses is parentheses. But if parentheses is less than 0, then the absolute value is computed using this formula. absolute value of parentheses is the negative of parentheses. So in other words, to be clear, the absolute value symbol can mean different things depending on whether the thing inside of it is known to be positive or negative or zero. Now, because the absolute value symbol actually represents a piecewise defined function, then this given one-line formula for f of x, this thing, also represents a piecewise defined function. Let's figure out how that function behaves. Well, if x is greater than 11, then x minus 11 is greater than or equal to 0. So this expression, absolute value of x minus 11, would be computed using the formula x minus 11, because the absolute value of something that's known to be positive is just that thing. So in that case, the expression for f of x would simplify. So the given expression is this, but then we replace this part of the formula, absolute value of x minus 11, with just this, x minus 11. Because again, x minus 11 is known to be positive, so the absolute value of x minus 11 is just the same as x minus 11. And then from here, we know that we can cancel x minus 11 because x minus 11 is not equal to 0. That's that very important concept from the first month of calculus. When can you cancel and when can you not cancel terms? This term is known to not be 0, so we can cancel it and we get the number 1. So the conclusion is that if x is greater than 11, then f of x equals 1. Now what about another case when x actually equals 11? Well, in that case, x minus 11 equals 0, so the absolute value of x minus 11 would just be the absolute value of 0, which is 0. So in that case, the formula for f of x would simplify. So f of 11 would be this, 11 minus 11 divided by the absolute value of 11 minus 11, but that's just 0 over 0, and that's undefined. Third case is when x is less than 11. Well, in that case, x minus 11 is less than 0, and so to compute the absolute value of x minus 11, we use this formula. We find the negative of x minus 11, because again, the thing inside is known to be negative, so we compute the absolute value of that thing by taking the negative of that thing. So in this case, the expression for f of x simplifies. So f of x, which is given by this formula, would simplify. We would replace this expression with this expression. The absolute value of x minus 11 is equal to the negative of x minus 11. So that gets us to here. Now we can cancel at this point because we know x minus 11 is less than 0. That tells us that x minus 11 is not equal to 0, so we can cancel x minus 11. And we end up with this surviving minus sign. So the end result is if x is less than 11, then f of x is equal to negative 1. So summarizing what we've just found, we've found a three-sentence description of f of x. That is this. If x is greater than 11, then f of x equals the number 1. If x equals 11, then f of x is undefined. If x is less than 11, then f of x equals negative 1. Well, those three sentences can be sort of condensed into this symbolic expression. This would be spoken f of x equals x minus 11 divided by absolute value of the quantity x minus 11, which equals 1 when x is greater than 11, which does not exist when x is 11, and which equals negative 1 when x is less than 11. So here is a condensed presentation of the formula for f of x involving a piecewise presentation. Here is a prose description in words that's going to be more useful for us in this current problem. Now let's go back up and remind ourselves what we're supposed to be doing here. Our job is to do these 5 things using this function. All right, well, question A says find f of 11. Well, f of 11 means we substitute x equals 11 into the formula for f of x. Here I've omitted the absolute value symbols. And the result is we get that f of 11 reduces to this expression, which is undefined. So this symbol does not represent a real number. So f of 11 is undefined. Question B was to find the limit as x approaches 11 from the left of f of x. Well, we start by writing down this symbol, the limit as x approaches 11 from the left of f of x. Now remember that this symbol tells us that we should be considering x values that are getting closer and closer to 11, but less than 11. Well, for those x values, the formula for f of x is f of x equals -1. Remember, we found this description of the function f of x in sentences, 3 sentences. When x is less than 11, f of x is computed using that formula, just simply f of x equals -1. So we've written down the left side of our computation. That is, we've written down the thing that we're supposed to find. Now we use the appropriate formula for f of x. That is, f of x is just the number -1. So we've swapped that out in our limit expression. We still have, though, the limit frame around that. We're finding the limit as x approaches 11 from the left of -1. Now let's zoom out. What we've got here is the limit of a constant. Let's go back up and look at our limit properties. Remember that Theorem 2, Part 1, which I would call Theorem 2.1, says that if you have a constant k and you're finding the limit as x approaches c of k, well, that limit is just simply k. So back to our limit computation, here we have the left side of Theorem 2.1. We have the limit of a constant. Theorem 2.1 says we can just simply replace that whole thing with the constant itself. So that number -1 that was sitting there is what we put there. So we found that the limit as x approaches 11 from the left of f of x equals -1. Notice, as I've mentioned before, it's very important that you use the limit symbol correctly. Our original expression, the thing we're supposed to find, involved the limit. The next thing we wrote still had the limit expression because all we had done was we'd swapped out f of x for the correct formula for f of x. It wasn't until later, after we used Theorem 2.1, that we wrote something that did not have the LIM symbol in it. Let's go on. Question C, we're supposed to find the limit as x approaches 11 from the right of f of x. Well, that symbol, x approaches 11 from the right, tells us we should be considering x values that are getting closer and closer to 11, but greater than 11. Well, for these x values, the formula for f of x is this: f of x equals 1. Remember, when x is greater than 11, the formula for f of x is f of x equals 1. So to compute our limit, we start by writing down the expression that we're supposed to find, the limit as x approaches 11 from the right of f of x. And then we swap out this f of x with the appropriate formula for f of x, which is just the number 1. So we still have that limit expression, we just replace the f of x inside of it with just the number 1. Now we zoom out, we have the limit of a constant. Well, Theorem 2.1 tells us that we can replace that limit with just the constant. So the result is this limit is the number 1. Question D says to find the limit as x approaches 11 of f of x. Well, that's simple. This limit does not exist because the left and right limits don't match. The limit from the left was -1. The limit from the right was 1. So those left and right limits don't match, and therefore the limit does not exist. Question E says to illustrate with a graph. Well, the formula for the function f of x is that single line expression, but the sentence description is more helpful for making a graph. We have this 3-sentence description. When x is greater than 11, f of x is equal to 1. So you can see here I've made a graph where to the right of x equals 11, the graph is a straight line with line equation y equals 1. If x is less than 11, then f of x equals -1. Well, that's shown here. For x values less than 11, the graph is a straight line with line equation y equals -1. And when x is equal to 11, f of x is undefined. You can see that is shown here. Both of those locations, 11, 1 and 11, -1, have open circles, so the graph has no y value when x is 1. Now the job for question E was not to make a graph of f of x. The job was to illustrate our earlier results with the graph. So let's go back up and look at our results. The result of question A was this: f of 11 is undefined. Well, how do we illustrate that on this graph? We should draw our reader's attention to the fact that when x is equal to 11, there is no y value. We should actually write that on the graph. So I would consider that an illustration of the result of question A. Point out that how does it show up in the graph that f of 11 does not exist. Now, how do we illustrate question B? Well, question B, our result was the limit as x approaches 11 from the left of f of x was equal to -1. Remember the graphical significance of that. That means that the graph is heading for the location 11, -1. That's the x and the y coordinate of a location that the graph is heading towards from the left. Well, we can see that's going on here, but we really should do something that draws our reader's attention to it. These little arrowheads I like. They make it clear that the graph is heading for this location. But I want to be even clearer. I want to write some words so the reader will definitely see what I want them to see. So the graph is heading for the location xy equals 11, -1 from the left. That's my illustration of the result of question B. Now, how do we illustrate the result of question C? In question C, we found that the limit as x approaches 11 from the right of f of x was 1. Well, recognize that in that sentence that I just spoke, there's an 11 and there's a 1. That 11 and that 1 are the x and y coordinates of a location that the graph is heading for from the right. So to illustrate that on this graph, I will highlight that behavior. And again, I'll write some words. So there's my illustration of the result of question C. The graph is heading for the location 11, 1 from the right. Notice that I did not use the word point. I said the graph is heading for the location xy equals 11, -1. Notice there's no point there. We definitely would not have been correct to say point. But even if there was a point there, I would still say the graph is heading for that location. The idea is that the limit expression is about the trend. It's not about what actually happens when you get to 11. And here I wrote the graph is heading for that location. Well, that's the end of that example. Well, that's the end of the video. Thank you very much.